Electric traction is the most efficient way of hauling trains. It's capable of dealing with heavy loads at high speeds with magnificent acceleration, taking steep climbs in its stride. Britain has had electrified lines for many years, mainly in densely populated areas where frequent stopping and starting make acceleration important for maintaining good overall speeds, and on some short main lines like the Manchester-Sheffield-Wath line with its stiff gradients over the Pennines. Nearly all of these that drew their supply from overhead equipment used direct current at 1500 volts. France, too, had started to electrify her main lines using DC at a similar voltage. Then, as an experiment, her engineers tried using a 25,000 volt AC supply, first with AC motors, then DC motors with rectifiers installed on the locomotives. The experiment was a success. The system was cheaper because it needed less feeder equipment, the overhead wire could be thinner, saving copper, and because of this the supporting structures could be lighter, saving steel. So Britain decided to follow suit when electrification of more main lines was under consideration as part of the modernisation plan for British Railways. The first to be chosen were the old London and North Western routes between London and Liverpool and Manchester, the busiest line in the country where the demand for higher speeds and increased traffic was greatest. Paradoxically, the least important part of the network was the first to be completed. Traffic on the Stile line for most of the day is very light, and it was ideal for trying out trains, proving new signal and telecommunication techniques, and making drivers and operating staff familiar with them. In fact, it became the testing ground for almost every facet of electrified line working over the whole system. Usually, towns which the railway serves are also supplied with power from the grid, so there will be many places where grid substations are close to the line. At the substations, the grid's 132 kilovolt bulk supply is transformed down and fed to the railway at the required 25 kV. The transformers belong to the Central Electricity Generating Board, but in some places, as here at Acton Lane, where they have had to be specially installed, the railway has carried out the installation. From the CEGB's transformers, current is carried to the railway's line-side feeder stations by the shortest cable run possible. Ideally, feeder stations want to be about 25 to 30 miles apart. This is a normal sort of distance between towns served by the grid. Each feeder station serves one stretch of line between track sectioning cabins. Neither they nor the feeder stations are manned. The switch and control gear they contain is all remotely operated from electric control rooms. Turning a key in the control room sends coded impulses through circuits and relays to the cabins miles away. The light on the display in the control room shows the state of the circuit breaker in the cabin. Turning another key gives instructions to close. And automatically the report comes back that it has been done. There are only 3 electric control rooms for the whole system. Here at Crewe for the northern sections of the line, at Rugby, and at Willesden. They operate 12 feeder stations and their associated track sectioning cabins. From them, current will be fed to the overhead lines. But before they can be installed, the whole system must be re-examined for what is out of date in relation to the new, faster, longer, heavier trains that will be using it. Stations that have grown haphazard over the years, of which Birmingham New Street is a good example, a maze of platforms and running lines and footbridges and sidings. Manchester London Road, now renamed Piccadilly, is another, and of course Euston itself, for many years scheduled for reconstruction. With 15 platforms and innumerable sidings both inside and outside the station, with a new Euston station under construction, a complete remodelling of the track and signalling was needed when electrification was on the way. This immensely complex job interrupted services at Euston for only 2 weekends, during which her regular trains were diverted to other terminals. Here, an unfamiliar bustle. Euston deserted. Or was it? To eliminate the conflict at junctions where lines must necessarily cross one another, new flyovers were devised, like this one at Rugby, where the up line from Birmingham is now carried on a concrete viaduct. Trains going north towards Nuneaton can pass unhampered. Many bridges were too low for the overhead equipment. In some cases, a new bridge could be built on top of the old one. At Cheddington, it was built alongside. The old bridge was then demolished bit by bit by a series of controlled explosions, so that some tracks were always left clear for trains to run. Some bridges, like one here at Willesden, were cut and complete sections of deck lifted on jacks. New supporting girders were then put in on top of the old abutments. All this without interrupting traffic either below or, for the pedestrians anyway, above. In some cases, the level of the underside could be raised by putting the services normally carried between road surface and underside, drains, telephone cable conduits and so on, in a separate structure beside the bridge, and putting the deck back on precast concrete beams, taking up much less space. Over 400 bridges were reconstructed or lifted. One major bridge was taken away completely, the old familiar iron bridge just outside Euston, which would have been very much in the way of the redesigned track layout and overhead array. The social service it once performed was ended, so it was expendable. Only one series of tunnels on the whole network proved unadaptable. The 3 Harecastle tunnels at Kidsgrove on the North Staffordshire border. They were not wide enough for the clearances demanded by new safety standards. They were very wet in places and were costing something like £20,000 a year for upkeep. To have rebuilt them would have meant closing a busy main line for maybe a year. Single line working was impracticable. So the short Harecastle North Tunnel was opened up and braced with concrete crossbeams. The old tunnel was afterwards demolished with explosives. The middle and south tunnels, with a combined length of over a mile, were to be completely bypassed by a new tunnel only 238 yards long, climbing with a gradient of 1 in 80. No problem for an electric haul train, to a summit level at the south end. From there, the new line runs downhill in the open to rejoin the old main line just north of Longport. But for the most part, railway electrification is not like a normal construction job where the site can be cleared and then work begun. On this job, the site is already in use. The permanent way is already there. And what's more, services must continue to use it while the work goes on. But because the permanent way was already there, new mechanized erecting techniques could be devised and sophisticated machinery made up into working trains to carry them out. First on the scene is the borer train. The auger drill is carried on a low loader. A single diesel hydraulic power unit, by means of selectors, carries out all the operations necessary to bring the drill shaft to its vertical working position and locate the bit precisely. There are different sizes of bit to make holes for different types of mast, carried on an equipment wagon as part of the train. Following up will be the concreting train, with hopper wagons for cement, sand and aggregate. A mixing and pouring unit, and a power unit. In the hole made by the auger borer, a framework has been set and it is now concreted in. There are other types of upright mast which are set directly in the hole and concrete poured round them. Reinforcing rods go in. To the frames, the masts for this kind of portal-type structure are bolted. To them, in turn, the cross booms are fixed. For 2 and even 4 track spans, the booms are of quite modest size, but where the portal must span a great many tracks, they will be very large. The erecting train consists of wagons normally used for carrying steel and a diesel-electric crane, in this case an 8.5-tonner. Finally comes the wiring train. 2 flat trucks with wire drums on them, paying out the wire as the train moves slowly forward. 4 old coaches with flat tops built onto them for the erectors to walk on and still stay in the same place. The catenary wire, from which the contact wire is suspended, has gone up first. Now the contact wire is being hooked onto droppers dangling from the catenary. The droppers are made down below in the train's own workshop. The contact wire is then clamped to the register arms already in position on the supports. The register arms keep the contact wire in the right place relative to the track and give it the stagger which minimizes wear on the pantograph. The end result of all this will be passenger trains maintaining 100 miles an hour over considerable distances and 1,000-ton freight trains able to haul their loads anywhere, almost irrespective of gradients, at sustained speeds too. Speeds and loads of this order mean that track must be as nearly perfect as it can be. Track on wooden sleepers was lifted, taken away for less onerous duties and replaced, first with 60-foot lengths of flat-bottom rail on pre-stressed concrete sleepers, depot pre-assembled to the correct gauge for the rail and correct spacing for the sleepers. It's laid with great speed by the special twin side boom crane. The newly laid track is reballasted and left for a week in service to bed it down. Then the 60-foot lengths of rail are replaced with continuous welded rail. It comes in 720-foot lengths. It's fed from another special train straight into place on the concrete sleepers, as the 60-foot lengths are prized out. Continuous welded rail gives a quieter, smoother ride and is far more economical to maintain. Back along the line, a welding train follows up to weld each 720-foot length to the next on those sections which are arc welded. More recently, thermit welding, carried out by sight gangs, has been used. At each end of a continuously welded section, the rail ends are tongued to form an overlapping adjustment switch. High speeds and heavy loads make traditional signaling equipment out of date. Semaphore signals, partly obscured by overhead electrical structures and equipment, are hard to see. Color light signals are not. For safe braking distances on lengths where trains will be running at top speed, 4-aspect signals with their double caution are essential. The block system of passing a train from signal box to signal box all down the line isn't suitable for trains traveling at 100 miles an hour. So the signaling system of the network has been mostly concentrated into 19 power-operated boxes, the majority like this one at Rugby, and 200 mechanical ones have been abolished. Interlockings are remotely controlled electronically. Miniaturization has simplified the control gear to the point where it is often no more than a line-side black box, and has made consoles and display panels covering a wide area very compact. But in the relay rooms, equipment and wiring have become infinitely more complicated. This is just part of the wiring in the new box at Euston during its installation. The changeover from an old to a new signal system, wherever it occurs, must be carried out with the greatest precision. The signals and telecommunications engineers would like all trains stopped for, say, 48 hours to give them absolute possession of the tracks. But on a busy through line, as at Rugby, that just isn't possible. Essential trains have to run.
In order to enable the signal engineer to take possession of the lines detailed in Appendix A at 6 p.m. on Saturday, September the 12th, all signals at the undermentioned signal boxes must be set to danger and the points set for the routes indicated below. All points facing and trailing to be secured by clip and padlock. Rugby number 1, down Northampton to down platform. Up platform. When this has been done, an entry will be made in the train register book that all points and signals have been disconnected and the interlocking disarranged. Hand signalmen will be appointed at locations shown in this circular and will exhibit a red hand signal and place 3 detonators on the line to stop the approach of a train. The signalman must instruct the driver to proceed to the next hand signalman and must hand the driver a written notice duly signed by the signalman concerned. Thereupon, the hand signalman will allow the train to proceed by showing.
During the Sunday of that weekend, 17 mainline trains were passed through Rugby in this way. 6 o'clock on Monday morning. The new box had taken over. Of the new power boxes, Rugby covers the largest track mileage of any, west to Coventry, south to Wolverton, and north to Nuneaton, a total of 59 route miles. And the miniature cathode ray train describers show on the display the position in the area of every train and identify it by its head code. Each of these power boxes is connected with the others, direct by telephone and teleprinter, and by telephone to traffic control. After working trials of the prototype locomotives on the first electrified sections to be completed, from the designs on trial, one standard specification was evolved. Some are built in British Railways Doncaster Works, with electric gear by a number of contractors. Others are wholly built by contractors. In the locomotives are installed the big transformers and the rectifiers to bring the 25 kV AC supply from the grid to a working voltage of around 900 volts DC for the traction motors. At Derby Works, the new electric multiple unit stock is being built. These are the trains that are to be used for commuter services with a top speed of 75 miles an hour. But none of the new trains are permitted to run until each completed section of the line is inspected by Ministry of Transport officials and by the railway's own experts. Every inch of overhead equipment is scrutinized. The behavior of the pantograph is observed on closed-circuit television. The wires are looked at from the flat roofs of the observation coaches.
Stop!
In tunnels, clearance between overhead equipment and roof must be not less than the 8 inches required by MOT regulations. A specially designed spring-loaded support allows contact wire-to-rail height to be reduced to ensure this. 16 feet is the standard height of the contact wire above rail level, which may be reduced to an absolute minimum of 13 feet 9 in tunnels. As each section of the line was completed, it was opened to commercial and passenger services, from Manchester to Crewe, from Liverpool to Crewe, to Stafford, to Nuneaton, to Rugby. Then at last the wires were brought into Euston through a long, cold night in March 1965. On the 25th of October 1965, the last section into Euston was energized, and on the 3rd of January 1966, regular services began from London all the way to Manchester and Liverpool. In 1966, faster timings with the introduction of the new timetable on the 18th of April and completion of the remainder of the lines to be electrified in the network. To Coventry, to Birmingham, where New Street and Snow Hill stations are being combined, thence to Stafford, and up through the 5 towns to Macclesfield.